Hi, my name is Alexander Trautsch. I'm going to present an article published in Empirical Software Engineering I authored together with Steffen Herbold and Jens Grabowski with the nice name A Longitudinal Study of Static Analysis Warning Evolution and the Effects of PMD on Software Quality in Apache Open Source Projects. Now, as part of the introduction, I'm going to talk about the parts of this title. So first of all, what are static analysis warnings? If you program in Java, you may have seen this or a similar view. The static analysis warnings are the little yellow triangles at the bottom, warning me here, for example, that the cyclomatic complexity is too high or that I'm not closing a resource properly. The warnings that are displayed here are from a tool called PMD for Java, which belongs to a family of tools called automated static analysis tools. These tools can scan the source code without executing it, transform it into internal representations to reason about it, and then warn the developers about common coding mistakes, design anti-patterns, code style violation, code smells, and so on. Now, what is static analysis warning evolution? Well, if we scan the source code of a project retroactively for all past revisions with one of these tools, we may ask ourselves, is the number of warnings over time, is it going up or is it going down? Or maybe is it going up and down? And if it is going up and down, we here, for example, what happens at these points where it is going up or down? Now on to the quality part. We can divide software quality attributes basically into two different types. We have internal quality attributes and external quality attributes. The internal quality attributes are developer facing, basically what the developer sees of the source code. Size, complexity, coupling metrics, and static analysis warnings. The external quality attributes are developer facing. So we have, for example, bugs as the most important, but also usability issues, efficiency, and so on. In this study, we are exploring both kinds. With the internal quality attributes, warning density, we are using warning density. For external quality attributes, we're using defects as the most important one. Now on to the research questions. So the first research question is obviously, how are static analysis warnings evolving over time? To be able to answer this, we are first extracting a commit path from the graph. We are selecting only one path through the graph from the latest master commit to the earliest orphan commit. We do this because we have to exclude release branches that are not merged back into master, because otherwise we would have two different states of the repository which are working in parallel, interfering with each other, and we need a date-ordered representation of the static analysis warnings. The static analysis warnings are extracted via our SmartShark infrastructure, and then we are calculating the warning density. Onto the warning density, we fit a simple linear regression to determine the trend. Now, the second research question is a bit more involved. Here we want to know what is the impact of PMD, not only on the static analysis warnings themselves, but also on the number of defects. To be able to answer this, we are parsing all Maven build file information in the project. This also includes fetching possible parent POMs from Maven Central for each project, because the parent POMs also contain information about reporting and plugins that contain these static analysis tools. And we need this to be able to see when this tool was used or when it was not used, and also information about custom configurations. This is important for the second step. First of all, we are discarding commits where Maven was not used. This is the case for some projects in the beginning where they switched before they switched from Ant to Maven. Then we are building groups of warnings. We have the group of warning, for example, for only these warnings that the developers actively enabled via a custom configuration, and also a time-based group, which restricts all warnings to those that were available at that point in time where the commit was made. This is made possible by the very extensive changelog that PMD provides. Then we are fetching the defects from the Apache Jira for the project and calculate also the defect density. Now, to summarize the data for our case study, we have about 50 projects, about 100,000 commits, data from 2001 to 2017 including, about 200 PMD warnings, and we are restricting all files to only production code. We exclude tests, examples, documentation code because we are only interested in production side. Now on to the results. Here's our example from the introduction. This is from a project in our data called Calcite. We can see when we show all data that there is a lot of code added before 2015. And also the warning density goes up. This is the yellow line. And then we can see that there are some small corrections were made. Some code is added, but the warning density goes down. So there were some corrections made. We can also see that after 2015, before 2016, a large chunk of code was added to the project, which had more static analysis warnings, so the warning density also goes up. And we can also see that while the code was in there, the defect density was lower. It was higher when it was added and removed. Another example is from a project called Commons Collections. Here we can see that in the beginning of the project, the initial phase is a lot of code is added and the warning density is high. Then it evens itself out, and we can see that about 2010 PMD is added, and then the warning density goes down. But not in all cases. We can see before 2016 the warning density goes up again as code is added. Now back from the examples to summarize the results for the first research question. First of all, we found that logical lines of code and the number of static analysis warnings are correlated. We also found that generally the sum of the static analysis warnings increase while the warning density decreases. Not the case in all projects, but in most. From the warning types that are decreasing the most, there are naming, brace, and design rules. If we combine all of this data, average everything out, we can say that on average each project resolves 3.5 static analysis warnings per 1000 logical lines of code per year. So if we think of code with less static analysis warnings as higher quality code, we can see that the code in our case study projects is getting better. Now on to the results for the second research question. We found a positive trend after including PMD. However, regarding the deep warning density, most projects had a positive trend. So therefore, we did not really find an impact of PMD on the warning density itself. There was a small effect regarding the plain sum of static analysis warnings, but not the warning density. We also found that the custom configuration for PMD does not seem to have an effect on the impact of PMD. However, we found that there's a small but measurable impact of PMD on defect density. So if we divide our data into years and split it up into years in which PMD was used and PMD was not used, we can see that there's a lower density in years in which PMD was used. However, this is still a very coarse-grained result and also still an area which we work in. To summarize the article, we did a retrospective long-term study of the evolution of static analysis warnings in production code. We measured the impact of PMD on internal and external quality via the warning density and external quality via the defect density. If you want to look at the plots that are used in this presentation, you can go to this website. There's also a link to the paper there. And there you have a bit more information and can, for example, hover over the certain points where the warning density goes up and goes down, and you can look at the data. That's it from me. Thank you for your attention.
Possible questions you may have about his great paper. So far we have one question from Wouter Grunebale. Sorry for the surname, so sometimes I cannot pronounce them properly. So he's asking, why would you exclude test code for this? Unit tests and the restructuring of those is sometimes more important than production code. In my experience, code smells are also prevalent there.
That is definitely true, but for this paper, we were really only interested in production code, so the code for the application itself. And we think that production code is probably different from its structure than the test code, because in the test code you have to keep it simple and to the point. You don't really have a lot of branching in the unit test functions, for example. And so we expect a difference, and we were more interested in the real application code than in the test code. But of course, you could also have a lot of static analysis tools run on the test code and inspect these warnings. But they would probably be different from the production code.
Okay, thank you very much. We have another question from Mauricio Anice. He's asking, well, first he is giving you thanks for the presentation. And based on your case study, what are the lessons learned for other software development teams?
I would say that if you are using a static analysis tool, you should take a look at the rules that are enabled and make sure that the rules that you enable for the project are a good match for your project. Because this is important for the developer acceptance. So if you have a lot of false positives because of warnings for a logging library you don't use in your project, this is a problem. So I would say one of the lessons learned is that when you are using these tools, you are using your own set of rules. And this is basically also what these tools are telling you to do.
So, okay, Wouter is giving us a clarification. He says, so no quickstart.xml then?
No, I mean, sure, you have your point to start. So if you're taking the new, for example, PMD version, you have, I think, 300 or 400 rules. So a good place to start would be to take a look, for example, at what the Maven plugin enables by default. So that would be a good place to start. But it would definitely not hurt to scroll along on the rules and say, okay, this is something that I have noticed in the code and this is a problem. And these can be all kinds of things. So we have focused here on a general purpose static analysis tool. This is not something that is focused on finding bugs, like spot bugs, find bugs. This is a general purpose tool which also has something like naming conventions, class naming conventions, variable naming conventions, and so on. So if you want to have a uniform readability of your code, take a look at the rules and then enable only those rules that you think are worth.
Okay, so thank you very much. Mauricio Nietzsche is answering again. He says, interesting, that totally matches with our findings when we studied the ES-Link ecosystem and how big OSS projects use it. And then he's sending a link where maybe we can see the results he's mentioning. So far we have 6 minutes to go. No more questions, at least for the moment, but we have time for more questions if you want to ask more. And in the meanwhile, I think I can ask you maybe a question until somebody else asks. So I have some curiosities and also a doubt about some slides. So in the case of figure 6, but it also happens, I think, in figure 7 at least, the defect density seems to be 0 before 2015. And you mentioned something in the presentation, but I think I didn't have enough time to get it, or I was unable to get it. So can you explain us again what happens before 2015? Because I didn't quite get to understand.
Yeah, that's simple. The data wasn't there. So we are focusing on the Jira issue tracking system here, and it was not in use before that time. Actually, it was in use in that year. We are discarding the first year, and for the analysis of the data, we are discarding everything where it was not used. So for this visualization, the data is still there, but for the analysis, we are discarding this data.
Okay, so no new questions coming in, so I will keep on asking more things. When I saw the curves, all of them in general, to me it was not expected, I think, but it seems that according to your conclusions, the behavior that you see in the warnings, it's somehow, it makes sense, okay? Because I expected, like the warnings go down with time, the density. So can you explain us a little bit more, or kind of summary of what is acceptable and what is not?
That's different. That's complicated. Because what is acceptable, there are very huge differences between the projects, and not only some projects use PMD and some projects don't use PMD, there are still huge differences between projects who use PMD. So it is not really used uniformly. So as I was starting this, I was expecting, okay, I have just the sum of warnings over the states of the history, and if PMD was introduced, then it goes down. But that is not the case at all. So the warning density goes down, but this is regardless of PMD, and the sum of warnings almost uniformly go up.
Okay, thank you. We have a new question, and if you have more questions, we still have 3 minutes to go, so we have time for that. So Lutz Sprecher is asking, what is your interpretation of your data? How useful is PMP output in principle? How do project members treat PMD output?
So in our data, we can see that there are sometimes warnings resolved. It is not a continuous process I was expecting. So if you have this kind of tool, you can plug it into your continuous integration system or into your IDE with a shared set of rules. And I thought that the warning density the warnings would go down. But that is not the case. What we instead see is that at some points in time, some reviewer perform a cleanup, and then warnings are resolved.
Okay.
And so the usefulness for the output is, well, some members use the output and some do not.
Okay, thank you. There's another question, still 2 minutes to go. So interesting topic according to Wouter Gronebel. So I hope I said your name better this time, Wouter. I wonder, is there any future work planned related to this? So what are your future plans for the work?
Yeah, so we are currently working on more in this regard. Especially we want to have some kind of connection between warning density and bugs in the software or defects. We have here the defect density, but that's very coarse-grained per 1 year. So we are using some tools of software engineering research, in this case, fine-grained just-in-time defect prediction, because that is using the evolution of the software project for files, and we can map this then to defects. And this is something that we're currently working on.
Okay, so but it's you are already working on that, or is a future thing?
No, I'm already working on that.
Okay, so thank you very much. So it seems that Wouter liked your answer. Thank you, Wouter. I am trying to improve my skills in saying names in different languages. So there are no more questions so far, and there's only 40 seconds to go. So I'm not sure if I don't think that's enough for even a quick question. So thank you very much, all of you, for attending. Thank you very much for your great questions. And as you can see, you have a lot of clapping hands, Alexander. So you will be moved to the discussion room in case you want to talk a little bit more with Alexander about this wonderful work, this great work that he has performed. Okay, and thank you for attending the session, all of you.